Guchuan from Michigan University, who will be telling us about formal groups.
Yeah, so the talk is about formal groups. Yeah, so as last talk we see there is a deep connection such that between the homotopy theory and algebra. So on the homotopy theory side, we have the complex cobordism theory, and the upshot is this one admits the universal formal group law. So then, like everything on this side algebra about the structures of formal group will this deep connection, like Quillen's theorem, can pass to the homotopy side or the topology side, and that gives all the like all the pictures, like all other important players in the chromatic homotopy theories, like typical, like namely like the filtration, like the height filtration, and everything comes from the algebra of formal groups. So in this talk, we'll introduce some basic information for formal groups that we need to carry on the story. And also along the way, we'll also like prove something like promised in the first lecture. Yeah. So now like we got a definition of formal group from the first talk, and so maybe like one thing is, let me make the definition. So if we say a map between two formal group laws, and let's say we have a map from a formal group law F to a formal group law G. And what does it mean? This is a formal power series. Formal power series. Let's see, call it F and G used. Well, let's call it H. So this one has X plus higher terms. The first term should be X, such that it satisfies the following. If I use my if you use my source F to formally sum them together, then I can plug in my formal power theory. This will be the same as I apply G, but inside I apply theta X and theta Y. So this is a map from between formal groups from F to G. And in particular, we have seen this before. So namely, we construct many new formal groups by starting with a G X plus GY. And I take the G, yeah, this is H. And then I take the G inverse, where G is H, or maybe let me use H, consistent. Sorry, I just switched 3 letters. Yeah, so if I pick up my G to be the additive formal group law, then well, I can construct a new formal group law by this formula. That's what we have seen in the first talk. Maybe then let's see some examples. Maybe the easiest example, we have seen the additive one. Also, in Yutao's talk, we introduce the one that associated to the complex K theory. That's a multiplicative formal group law. Let's just say it's plus xy. In general, you can put any unit there. And for this one, it's called multiplicative because if you at 1 on both sides, you got this formula. And if I'm taking logarithm, then the right-hand side looks like additive. It's log. So you see, right-hand side becomes log x plus 1 plus log plus 1. So this formula, the situation looks very much like the above. Not this one, the one above. So this thing, this logarithm gives a map from the multiplicative one to the additive one, which is expected. And one can make it more precise. Actually, from this one, you can solve the logarithm formula. Well, this is just like the same as you expect in the in the usual algebra we learn. So you just do the Taylor expansion. Since now everything is formal power series, like there's no conversion issues. So you just formally write down the Taylor expansion for the logarithm function, and then you will have this one. So notice this one, like you got the one on the dominator. So this actually does not live, like it lives in the rational, like it does not. So if you start, so this is actually in the rational part. And with this one, I can give a isomorphism from my additive formal group law to the additive one, from the multiplicative one to the additive one. And in general, we will call like if I can I identify my formal group law to the additive one, and this is a logarithm for my formal group law. In particularly, the formal logarithm is a logarithm formula for the multiplicative one. And so one of the promised statements from the first lecture is when we say the map, the Lazare ring maps to downstairs, like maps to the ring with Z drawing out BIs. I claim that after tensor with Q rationalized is isomorphism because the theorem is for any formal group law F. So say if I'm living in the rational, so let's say this over a ring tensor with the rational number. So then, like my formal group law is isomorphic to the additive one. And moreover, we know the isomorphism, we invent a name for it, is the logarithm. And so the logarithm formula is given by the following one. So if I denote, so notice F is this one, it's a function in two variables. And we denote F2 xy to be the partial derivative on the second variable y, and everything is formal. So just like you do the polynomial, then we have the proof, like the isomorphism is given by the following. Logarithm for logarithm function for f. So we can write it log f. So this formula is you do the formal integral, and so you just do the integral of this function t comma 0, and you integral with respect to t. So up to x, then it turns out to be a formal property theory in variable x, and this will be the logarithm. And to see this one, like just it's on Pike's definition. So what do we hope? We were hoping, let's just for simplicity call this one fx, and we hope fx satisfies the following condition. Hope. So I apply f to my fxy. That's exactly I apply fx. I apply additive formal group law fx plus fy. I hope this is true. So I can just the proof goes as follows. So first, as I prove this one is a constant function, and I can check this must be constant 0. So it's constant, and finish the proof. And just like when we show a function is constant, we can just do the derivative. So in particular, you just need to compute of this whole thing. And also, this one supposed to be 0. And that's exactly like why I construct using the integral. So it's just like the fundamental theorem. So maybe let me just leave this as an exercise. If you're like if you want to try something like fun, so you can try to check if you do the partial derivative for the function I defined above, and then you will see the partial derivative for both variables is 0, so it's a constant. And you can check because all the functions defined without the constant term, so it's actually constant to 0. So in particular, the function holds, and that's how you produce additive. But notice, like in this process, it will produce the denominator. So in general, if you're not over Q, if P is not invertible, this now holds. So like your logarithm simply has coefficients lies in R tensor Q, not in R itself. So over R is not isomorphism. And for the example, you can see from the usual logarithm, like it already contains something non-trivial on the denominator. Yeah. So that's a part for the for one thing like we use in the first lecture, and then the another part is. Second part is in the end we were trying to compute like using Adams special sequences to compute the homotopy groups of MU from the homologic groups of MU. So I introduced a lot of new notations like the the algebra and the co-modules and so many like new algebra objects. But all this all of them can be interpreted in a way in the formal group law world. In particularly, if I'm understanding in this way, so like the E2 page, or like the algebra data I need. G data for the computation. Is first like I need this H star MU to be a co-module over A star, but instead of thinking of A star as a cohomology theory, the standard algebra, which is the following. So recall, I define this guy as the following. But notice, so HF2, or let's work just at prime 2 this time. So there, like the reason I work prime 2 is commutative. Otherwise, it's graded commutative. So in this way, like I get rid of the sign. So this one, like classically, it had the formula. All this Cassay is there. But now like I can play the same trick. HF2 is complex oriented. So there are two orientations. Just like the second step I did for the Quillen theorem's proof, how can I interpret like E star mu as pi star of E of drawing all the BIs? BI is a change of the orientation. Here is the same. What is A star? A star is pi star of HF2. Which is just F2. Drawing a bunch of variables. And these variables will appear at the coefficients of the change of coordinates. So if I have orientation number 1 and orientation number 2, so in particularly, I can write the second one in terms of t plus orientation of the first one. But something different is, so in the case, if I'm doing E star of mu is a universal formal group law. There's no restrictions. I can just map my formal group law to another one. But here, like the target is HF2, so it also has to be additive formal group law. That put extra that put like more restrictions on this on the morphism coefficients. So in particular, because it's additive, so there's no intersection term x times y. Everything is purely x or purely y. So you want all the intersection term vanishes. So in particular, you only working over F2, you want all the power is 2 to some power. So instead of having all coefficients, you only have the coefficients with t to the 2 to some power, and those coefficients is ai. And if you recall the the rule for assigning grading, then you can say the ai has exactly the right grading with ci, and this gives the ci. So in this way, you can interpret the synodal algebra as the automorphism of the additive formal group. Because what I'm doing is I'm changing a new coordinates. So when I change my coordinate, so what I introduce is just like a morphism between formal group law, like the above. So I change my coordinates by h, and I get a new additive formal group law. So in particular, in this case, is hx plus y equals h inverse. Equals hx plus hy, and then you can just compare coefficients. You see h can only have non-trivial coefficients for t to the 2x power, and that's the interpretation for the A star. And now the tricky part is, from this interpretation, it seems like the action. So notice in the end we need action on this guy. Well, like A is the automorphism of the additive formal group law, so it can purely act on the H part, but that's not what we want. So here, we need something geometry, not purely from the algebra. So here, like actually, like if you wanna figure out, yeah. So maybe I should put the reference. This is from Ruiz notes, lecture 9. So interpret this one from this point. So here is really you need something geometry, not just formal algebra. So the synodal algebra action, what we know is this one like is some fact you need to recall. This one acts on the RP infinity. So you need to recall that this one, if I x on Rp infinity, which is cohomology. This is f2x. Then the corresponding coefficients, like I should send x to x plus a1 x squared plus a2x to the 4 and so on. So this is a fact we need to recall. And what does help us here is, once you know the Rp infinity case, you know the Cp infinity case, because you can include the real part in the complex part, which in turn gives a map the other way, since y to x squared to match up the degree. So from the action above, I can see the action on Cp infinity, which we know like mu is closely related to Cp infinity. And then like from this action, I can read off the actions on my BIs. So in particularly, in this case, so if for this one, I got a new function. Let's call it f1. For this function y, because y goes to x squared, so the action should just be the action on x and square. But on x, I know how it acts. It's the above formula. And the whole thing square. Since I'm over f2, so everything just powered. So this gives the action on Cp infinity. And furthermore, from here, I can read off the action. So one can read off the homology of mu, and then so we at least a structure theorem to start with it, like to show that H star mu is actually P star comodules and on certain generators, and that one can also be seen in this case. So the key point here is seeing well, in this language, you can even go fancier, like to algebra geometry language to think them as group schemes. And so, but basically what's happening is the same as P star goes to A star. And then the quotient is exterior algebra. But if you prefer, you can think this as a group scheme. So then the arrow reverse. This is a quotient, and this is a kernel. And since the map, like this one, just consists of all the Ci squares. So what's happening is you just purely square everything. So that's a Frobenius map. If you map x to the power p, which p here is prime 2. Okay. So you can also think in that way, but like essentially it's just this one. So the key point now here, is there any questions? Okay, yeah. So the key point is like, so you realize the like H star and mu has free P star action on those generators UI, where I is not of the form 2 to the I minus 1. So that's the structure theorem tells us, like in the previous lecture, which is like very complicated, but like here, it has a more like it has a much easier explanation in the formal groups. In particularly, so you can prove this result like very so like in a very precise way, like elementary algebra with polynomials. So so this is in lectures in lecture 9 of Lurie. So this is the same as saying, like, for any, you want to check the following fact. For any f, if I'm thinking this one, if I start with the coefficients in the ring Z with all the bi's, so I got my formula like the following. All the bi's are there. One can uniquely write it as a composition of two formal power series with the restrictions on the coefficients. So I want this one to be H compose G, my y, my Fy, and where like G is formal power series like with coefficients in all the AIs I introduced above. So this is a formula, and for the other part, H it admits properties that for the HI, like it drops all the terms of the format 2 to the I minus 1. In particularly, there's no terms y squared. It jumps to the next one, y to the power 3, and front yeah. Okay. So here, like, is all the bi for I is not of the format. So this is an elementary algebra. So you just need to check. So this happens, you can rewrite the F as a composition with two formal power series with the restrictions of the coefficients. In particularly, that's why, like, in the final answer, you can regard so as a consequence, so H star mu can be written as a tensor product, where one part I only have this, let's call it ui, and with I is not 2 to the power I minus 1. So the other part is just P star. So G is given by P star. That's how the action works on the on this additive formal group law. So this is the interpretation of the structure theorem from the last lecture. And so the other part, maybe like slightly harder, is a change of ring. So maybe let me also remark on that one. So, well, the change of ring, I think it might be helpful to directly think of the easy case, because the change of ring is something not very hard, but like I think the case is just everything's co-module, so that makes the thing looks harder. So maybe just think of the following examples that may help. So if you think of the group homology, let's see if you have the like extension of groups. So K is a normal group in G. So if you happen to compute the J homology, but with the coefficients, it's induction from the subgroup. So in this case, you can just simply compute the K homology with the smaller coefficients. So like notice the group homology can also be written as the EX groups. So the change of ring is basically what's happening is this one, but just like in the co-module world, everything is co-tensor and looks much more complicated than it has to be. Right? So you notice here, like this one gets smaller and than the before. So then what has happened in the previous case is also the similar situations. So but also like let me just advertise that in Lurie, like for the co-model case, like it's easier to think in the algebraic geometry language, because you will change the covariance once more. So the intuition on the algebraic geometry object is much more intuitive. It's just like the quotient. It's like the above. So I quotient the group by G. So I can first quotient by the subgroup K, and then the further quotient by the group G mod K. So that's exactly what's happening there. That gives an explanation of the change of ring in the co-module settings using the algebraic geometry language, which is much more intuitive than the previous structure theorem. And the rest is just like the same calculation. So, but like with this one, like you have the concrete action, and all the actions are just formal comes from the coefficients for all those formal group laws. And interpreting one thing very interesting is you see that one thing plays a key role here is automorphism of formal groups. Here is the additive one. And later on, we will see the automorphism of formal groups like plays an essential role in the chromatic homotopy series. Okay, yeah, so that's all I want to say for the last lecture. So like so far, we have been working over rational numbers, and we have the everything isomorphic to the additive formal group law. And now we want to switch into the interesting part. So now like we'll work over characteristic P. So in particular, yes.
Can I stop you and ask a couple of questions since you're starting a new section? Yeah. Can you go back to the first page? I remember you said something about like if you define the second orientation for the dual signal algebra, like those coefficient AI corresponds to zeta I. Like I was. Do you mean exactly equal? Because I think you mentioned like because zeta I came from like the RP infinity to the homology of RP infinity to dual signal algebra. Do they correspond? Like, are they exactly the same, or is they just have some relation?
They're exactly the same. Like maybe up to a potential deal, but they're exactly the same.
Yeah,
like,
because I think you basically
so the point
that,
is So the point is like A star, which is HF2 star HF2. This one can be also regarded as automorphism of the additive formal group law, and in particular, giving an automorphism of the additive formal group law is giving the data of the coefficients in the formal power series of change of coordinates, and data I appears as the coefficients. So the explanation is the same as in the previous case, like E star of MU for a general complex oriented E theory.
Right.
Like the E star MU is of the form pi star E drawing all the BIs. So it has two explanations. One, this BI is changing the orientation from TE to TMU.
Yeah.
The other explanation is all this TS has been computed, like all this BS coming from the CP infinity homology. So here is similar, like you can treat it as from CP infinity, which you can embed into the RP infinity. The other one, you can treat it as a change of the coordinates. So they're the same.
Okay. And another question. So like I think you wrote down so just say at an alternating. So it's like the dual signal algebra, half algebra, like as a half algebra equal to the tensor product of the polynomial part and the exterior part.
Yes.
Okay.
Yeah, that's the extension of half algebra. But the extension of half algebra has its own definitions, so I didn't fully recover the definition yet. Yeah, but like a reference for that one will be Green Book. Yeah.
Okay, great.
Like the point, like it's the coproduct formula for the P star part, like it's self-contained. So if you do the co-production on those cassettes, you only end up with cassette tensor cassette. You won't have
no costing. Okay.
But like if you do co-product on tau, like there will be cassette involved. But still, like the quotient of half algebra has itself own definition itself is not Hopf algebra. So just a warning.
Oh.
Like not all the three terms are Hopf algebra, extension of Hopf algebra.
So you meant the dual serial algebra is not a the
No,
exterior
so
part
sorry.
is not a Hopf
Maybe
algebra.
I just read this down. So in this one,
yeah.
All I'm saying is this one. We see this is a extension of Hopf algebra. Only these two are Hopf algebra. Like E is not,
Yeah,
because the co-product
right.
formula is not closed. Like
Yeah, you mentioned it involves something in P, so it's not a Hopf algebra. It's only a quotient of.
Yes, like if you do co-product formulas on those tau i's, like C will appear in the co-product formula.
Yeah, because I was thinking like a naive proof for that, like the atom spectral sequence for pi star mu. I was thinking I could just write A star as P star tensor like E star and then cancel T star and get the answer.
Yeah, like
that's
the intuition is right. Like just like with the co-modules, you need to also like compatible with the co-algebra, which makes it harder. Yeah.
Okay, great. Thanks.
Okay. Yeah. Right. So now maybe yeah, so we'll switch the in the remaining time, let me switch to work over not the rational one anymore, but let's do the p local ones. So let's over like the p localized integer. So the formal group plot over there. Well, so here then like I think the important definition is the p-typical formal group law. Since like in the opening talk, like if you recall, like you see there's one very important invariant about formal group law called heights. So the height comes from in the p-typical case. So the p-typical formal group law can be defined for a general CP algebra. But let me not doing it. Let me just do the easy version, or like the more intuitive version, like for the torsion-free case. But you can check for the general definition. So formal group, this formal group law over CP algebra, and let me just put the condition torsion-free to make life easier. But there are definitions for the general case. So the condition is, well, maybe let me see, p equals is a formal group law with the logarithm. So we just define the logarithm is this guy like isomorphic to the additive one, like what the formal power series is. That's the logarithm. And the point for this one, the logarithm has a format. Only the p to the power I appears in the coefficients. As we already see one example about like from the additive one to the additive one over F2, like at the form. So it's a formal power series with all the coefficients, but now like only p to the power I appears. It's not all of them. Well, L now should be 1, like it should always be x plus something. Okay. So this is the definition for p-typical formal group law. So like it's just like the general case, like I have a universal one. After I define the p local formal group law, I can ask for if there is a universal so first, like the definition makes sense. The remark is, or maybe it's like a theorem. I think this theorem of Katir. So it's saying like you can only study for the p-typical formal group law. That's enough because over ZP algebra. So notice like there's a definition for general case. So the theorem applies to general case. Just over any ZP algebra, like including there's torsion. So like all formal group laws are canonically iso to a typical one. Yeah, so maybe in somewhere you see the strict iso. That means just like the formal power series start with exactly x. yeah, in general definition, like an isomorphism could be start with a UX where U is a unit. So by this theorem, we know like we can only study the p-typical one. We don't lose anything, like because everything is isomorphic to p-typical one. So this is like the proof, like the idea. Maybe since the time, let's just say the proof. The idea of the proof is the following: is you show the universal one is p-typical. Where the universal one is just you do the universal formal group law, but you tensor with ZP, change the change the coefficients into ZP. Then like this one shows everything will be p-typical. But however, this will not just be, so this is a p-typical one, shows that one, but this itself is not the universal p-typical formal group law. So maybe an analog is in Anne's talk, you already see like the p-localization of MU splits as a bunch of wide of suspensions of Brown-Petersen spectra. So the p-typical one will be corresponding to the Brown-Petersen. That's the universal one. So in short, like the universal formal group law after p-localization is no longer, it's not universal, but like but it's just many copies of the coefficients will be the many copies of the actual universal one left over. Okay, and then I think maybe the next part, like let me get the important definition for height. So first, introduce some notations. So for a number n, I can define this is a formal power theory. So maybe let me just define the first one. This is just x. And the second one is x formal sum x, which is just f, xx. So this is given a formal group law f. So in particular, I can define n plus 1 from after I define n is a formal power theory. And then I formal sum x. So just like I put them in the spot of f. So this is another formal power theory purely in one variable x. So that's n plus 1 theories. So in particularly, so like if f is p-typical, then the p theory, like maybe you can denote f here to indicate this one depends on the formal group law f, is of the form x to the p to the n with the coefficients. Let me use Vn here. And the first non-zero 0 Vn. Let's see, this appears at some VH. That means all smaller previous VH minus 1 are all 0. So the number H gives the height. Okay, so this is the definition for the height. And so height is important from the algebra side. And the reason is it completely determines the formal group law if you are in a nice situation. So let's say, I think it's a theorem. If over a, let's say over a closed algebraic closed field, like so, p-typical formal group law of height n, all, let's say all p-typical formal group laws of height n are isomorphic to each other. So first we see over ZP, you only need to study P-typical formal groups, and later on we see like for if you are over a nice field, then all you need to study is like a height n formal group. That's all of them up to isomorphism. And just by definition, I can pick up a very easy one, which is called the Honda formal groups. Like it's originally defined over FP, but like in many cases, you can extend the coefficients to FP bar or FP to the power n as you want. But the feature for this formal group is this one is defined by the following formula. The P theory for the Honda formal group law is just x to the P to the n. That's it. Like by definition, this one has height n, or is height n formal. So for each head, there's a Honda formal groups from group laws, and it like the definition is determined by its P theory, which is just given by very simple formula. The simplest one could be x to the power to the P to the n, because by definition, the coefficients of f to the P to the power n, it's the first time the coefficients is non-trivial. So this one has height n. And this will be play a very important role later on. So all of these are just like algebra stories. And the punchline is from the formal groups, like over P local world, like what's important is the P-typical formal group law. And like the P-typical formal group law can be determined, classified by an invariant called height. Okay. So the height, like the definition, is just follows from the P theory of it. Okay. So that's for the height, the definition for the height. So we will see this one like is related to complex cobordism theorem and like the Braun-Petersen theorem in a minute. So maybe let me think. So in the remaining few minutes, which part I wanna cover. So maybe like due to time reason, let me just remark. Well, let me just state the fact and not like say more about it like this. So at the previous case, we say like something important is a single algebra which can be regarded as automorphism of formal group law. So again, so in this case, well, it's interesting to study the automorphism of the height n Honda formal group law. And like since it's isomorphism, this will gives everything, right? So this usually denoted as like also called the Morava stabilizer group. Which will be very useful later. So like it turns out this one will be of this format. As to the power n is P. Where let me just explain the notation. So this is a weight vector. So it's basically drawing P to the power n minus 1 roots of unity to ZP. And well, for this one, is A is in the coefficients weight vector. And A sigma, this is Frobenius action. So in particular, the weight vector admits a Frobenius action. And the point is this one is non-commutative. So this group will appears and plays a essential role in the later story. So like all these generators, the S and the relations, actually can be interpreted. So what's the action of formal group law to itself? It's just a formal power series, right? And how do you construct a formal power series? The easiest way is using the P series and so on. So basically, those S are constructed as some P series or some S series. Like, yeah. So maybe in the last part, let me say something about since half algebra and half algebra appears many times. So maybe let me see how does this one relate to our story here. So let's do the P-local version. So this usually think this is a P-local version of MU, although it's really just one copy of all those suspensions. But the point is, like, because this is complex oriented, and so this one is where the universal P-typical formal group law lies over. Typical is over the coefficient range of this Brown-Peterson spectrum, which let me just wrote it down. And as you can imagine, like those VIs has restrictions to particular degree, and they're actually like to the all the things should be to the power P to the N, and since we hope everything lies in degree -2, so you just have a -2 there. So this VIs lives in Vn lives in degree 2 times P to the power N -1. And just play the same role as change of the orientations. You can see this one must be the coefficients of BP drawing a bunch of variables. Originally it's drawing all the BIs, but now you can think you want to join all the TIs, which this is a change of the coordinates. And similar reasons, TI will have restrictions to this lies in this degree. So you have a pair of objects in here. And it turns out this will be half algebroid, which means it means a lot of structure map. So maybe in the meantime, let me just let me give the reference and state the result, and didn't say much more about the detail. So maybe see this one in C Green Book. Let me see. Did I copy where? So okay, so it's here. This is in appendix, like theorem 82.1.27. So basically the point is like BP star BP. Well, it's a half algebroid. So we have already seen if in the simple case, I'm not doing the fancy all P-typical formal group law. In the very simple case, I'm just doing the additive formal group law. This is a half algebra, which is this is A star, this is HF2. This is half algebra. And as you can imagine, just like this one, like this should be co-algebra, and there should be all the structure maps. So which is like listed in detail in this reference. So yeah, maybe in the meantime, I think it won't help too much if I just copy out the complicated formula. But like the point is like all the formulas for the VI and the TI, they have the interpretation of formal groups. Like all these formula, the structure, all this complicated recursive formula comes from like you do the power series, formal power series, and you do their compositions or other actions, and you compare the coefficients of the variables, and that's how you get all the formulas. So I think I'm running out of time. So maybe I'll stop here, just in the last 5 minutes for the questions.
Okay, let's thank Guchuan for the great talk.